Two rocky planets, same star, same age, same general size range. And right now, one of them appears to be holding onto a real atmosphere while the other shows no sign of one at all. That split isn't speculation. It's the result of years of careful, patient observation, and it's genuinely one of the most important comparisons in the search for habitable worlds beyond our solar system. Here's the setup, and it's stranger and more scientifically significant than a fabricated headline could invent, because the real version of this story doesn't need any embellishment to be worth your attention. About 48 light-years away, in the constellation Cetus, there's a small, quiet, roughly 3 billion-year-old red dwarf star called LHS 1140, also cataloged as Gliese 3053. It's orbited by at least 3 known planets, but 2 of them, LHS 1140b and LHS 1140c, sit close enough together and similar enough in size that astronomers have spent years directly comparing them, treating them almost like a natural experiment sitting right next door in cosmic terms. First discovered back in 2017, this system has quietly become one of the most closely watched laboratories in exoplanet science precisely because it offers something rare. 2 rocky worlds around the same star, close enough in size to compare directly, rather than scattered across entirely different systems with different histories. LHS 1140b is the more famous of the 2. It's roughly 1.73 times Earth's radius and about 5.6 times Earth's mass, sitting comfortably inside its star's habitable zone, the range of orbital distance where temperatures could allow liquid water to exist on a surface. It's also the second closest temperate transiting planet to Earth ever found, which makes it an unusually valuable target, close enough and large enough that its atmosphere, if it has one, is actually within reach of current instruments to study in detail. LHS 1140c is smaller and sits closer to the star, receiving significantly more radiation. Both planets straddle something astronomers roughly 1.5 and 2 Earth radii, where planets are unusually rare, thought to mark the dividing line between rocky super-Earths that have lost any primordial atmosphere and puffier sub-Neptunes that manage to hold onto one. Sitting right at that boundary is exactly what makes this system so scientifically valuable. These aren't planets safely on one side or the other. They're planets caught in the process of becoming one or the other. The first serious look at this system with the James Webb Space Telescope came in a 2024 study led by Charles Cadieux at the University of Montreal, using Webb's NIRCam instrument to study LHS 1140b directly through transmission spectroscopy, the technique of analyzing starlight filtered through a planet's atmosphere as it passes in front of its star. Because LHS 1140b's bulk density had come back lower than expected for a purely rocky, Earth-like interior, the team went in trying to distinguish between 2 real possibilities. A mini Neptune carrying a thin hydrogen envelope, or a genuine water world with somewhere between roughly 9 and 19% of its mass made up of water. During one of those observation windows, the team caught something they weren't specifically planning for. A serendipitous transit of LHS 1140c happening to cross the star during the same observing run, giving them an unplanned but genuinely valuable look at both planets using the same instrument under the same conditions, back to back. That original Webb data turned out to be messier than hoped. The combined spectrum showed a telltale signature of stellar contamination, specifically unocculted faculae, bright magnetically active regions on the star's surface that weren't directly blocked by the transiting planet, covering an estimated 20% of the visible stellar surface. That kind of contamination can mimic or mask genuine atmospheric signals, which meant the original Webb observations, while foundational, couldn't cleanly settle the question of whether LHS 1140b actually had an atmosphere at all. That's where the story picked up again in 2026, and this next part is worth being precise about because it didn't come from Webb. A separate research effort, led by scientists including Charles Cadieux, again and Shreyas Visapragada at Carnegie Science Observatories, turned to a different tool entirely. The ground-based Magellan Clay Telescope at Las Campanas Observatory in Chile, using an instrument called WineRed, a spectrograph specifically built to split incoming light into extremely fine detail across the near-infrared. The Clay Telescope's primary mirror happens to be 6.5 meters across, identical in size to Webb's own segmented mirror, but the advantage here wasn't aperture. It was the specific wavelength precision WineRed could deliver, precision that let the team hunt for a very particular signature: helium escaping from a planet's upper atmosphere, a signal that sits in a narrow enough wavelength band that catching it cleanly requires exactly this kind of high-resolution instrument. Helium escape matters because of a specific piece of theoretical modeling. Researcher Kauai Cherubim, during his PhD work, built a model predicting that lighter gases like hydrogen should escape a small, heavily irradiated planet's atmosphere faster than heavier helium, meaning any atmosphere a planet like LHS 1140b still has left after billions of years of stellar radiation, should be increasingly helium-rich, as the lighter gases bleed away first. If that model was right, helium escape wouldn't just be a curiosity, it would be the expected fingerprint of a genuine surviving atmosphere, essentially the chemical residue left behind after everything lighter has already boiled off into space over geological time. Observing LHS 1140b during a September 2024 transit, the team found exactly that signature, helium leaking from the planet's upper atmosphere, heated and driven outward by stellar X-ray and extreme ultraviolet radiation. The results, published in the journal Science on July 17, 2026, mark the first confirmed atmosphere ever detected on a rocky exoplanet sitting inside a habitable zone, a genuine milestone in a search that had, until this point, only ever found rocky habitable zone atmosphere holders. But the detail that makes this a genuine two-planet story, not just a single triumphant result, is what happened when the team looked at LHS 1140c using the same method. No helium absorption was detected at all, and it gets stranger. When the team went back and re-examined earlier data from 2025, they found that the helium signal from LHS 1140b itself had disappeared, present during the September 2024 transit, gone by 2025. That's not a contradiction or a mistake. It's evidence of time-variable atmospheric escape, meaning the rate at which this planet loses gas to space isn't constant. It fluctuates, likely in response to changes in the star's own activity, its X-ray and ultraviolet output rising and falling the way our own. Sun's activity cycles over roughly 11 years. Astronomers interpret this pattern as consistent with an upper atmosphere dominated by helium and depleted in hydrogen, with heavier volatile gases potentially trapped at lower altitudes. Exactly the layered, fractionated structure Cherubim's model predicted for a planet slowly losing its lightest gases first, while holding on to everything else. So here's where that leaves the actual comparison. Two rocky, similarly sized planets orbiting the same aging star, at slightly different distances and slightly different radiation levels. One of them, LHS 1140b, shows real, if variable evidence of a surviving atmosphere actively losing gas to space, in a way that suggests it's been fractionating for billions of years rather than disappearing entirely. The other, LHS 1140c, closer in and more strongly irradiated, shows no such signature at all, at least not yet, using the same detection method applied under the same conditions. Robin Wordsworth, a professor involved in interpreting these results, has pointed to something important about why this specific technique matters beyond just this one system. Because the helium detection method is ground-based rather than dependent on scarce, expensive space telescope time, it doesn't require competing for scheduling on an instrument as oversubscribed as Webb. Cherubim's underlying model can now be applied to other rocky habitable zone candidates to predict, in advance, which ones are most likely to show a detectable helium outflow. Planets that pass that filter become priority targets for exactly the kind of follow-up Webb observations that are expensive and limited, searching for water, carbon dioxide, and other gases that would matter far more directly for genuine habitability. That's really the significance sitting underneath this story. It isn't simply that scientists found helium leaking off one planet and not another. It's that they now have a working, testable filter for figuring out which rocky worlds are worth the enormous cost of deeper atmospheric study, and a real, in-progress example of exactly what a planet caught mid-transformation, still holding some atmosphere, still losing pieces of it to space, actually looks like when you can measure it directly, rather than model it theoretically. It's also worth being honest about what this discovery does and doesn't prove. Detecting escaping helium doesn't confirm LHS 1140b is habitable, and it certainly doesn't mean anyone has found water, oxygen, or any other biosignature there. What it confirms is narrower and, in its own way, more foundational, that a rocky planet sitting in a habitable zone can retain some form of atmosphere against billions of years of stellar radiation, something that had never been directly confirmed for any such world before this result. Every previous rocky habitable zone planet studied in detail had come back, either atmosphere-free or genuinely ambiguous. LHS 1140b is the first clear exception. And LHS 1140c-EOSC's apparent lack of any helium signature isn't necessarily a final verdict either. It could mean the planet genuinely lost its atmosphere entirely under stronger irradiation. It could mean any remaining atmosphere there is structured differently in a way this particular technique isn't sensitive enough to catch. Researchers have specifically flagged it as a target for continued observation, both from the ground and from Webb, rather than treating the current non-detection as the end of the story. Zoom out, and this is what a genuine two-planet transformation story actually looks like when it's built entirely from real, published, peer-reviewed data rather than invented drama. Not aliens, not a signal. Two rocky siblings orbiting the same star, sitting on opposite sides of a threshold that determines whether a planet holds on to air or loses it to space, one showing real evidence of survival, if unstable and still fluctuating, the other showing no such evidence yet at all. That's a genuinely dramatic scientific result on its own terms, built from a JWST dataset that first flagged the system as worth this level of attention, and a ground-based follow-up precise enough to finally catch the difference between them. It's worth sitting with how long this actually took to come together. The system was discovered in 2017. Webb's first detailed look happened in 2024, and even that came back complicated by stellar contamination rather than a clean answer. The helium detection that finally cracked the puzzle open didn't arrive until July 2026, built on a theoretical model, a purpose-specific instrument, and science. Years of layered, incremental work, each study building on the last, rather than a single dramatic reveal arriving out of nowhere. If you want to know what Webb finds when it goes back to look at LHS 1140C directly, subscribe and turn on notifications, because this is exactly the kind of real, sourced, still unfolding story worth following as the data keeps coming in.